Welcome to the second of 4 lectures on power system planning. I'm Hyde Merrill. This lecture is on transmission planning. This slide shows the 4 major points I'm going to discuss in this lecture. I'd like to begin by putting transmission in the context of the total power system. The investment in transmission is quite small compared to the investment in generation and distribution. The 2 principal purposes of transmission are to connect remote generators to the load, that is to local distribution systems, and to improve the reliability of the bulk power system. Let's look at the effects of transmission. First, transmission affects the bulk system reliability. Notice, however, that most outages a customer sees are due to problems on the distribution system, not on the bulk system. Transmission affects generation. It affects where power plants can be built, what kind of power plants are built, how they're dispatched, the use of renewable resources, and so on. Third, transmission affects the environment. There are obvious direct effects and there are less obvious indirect effects, because transmission allows the transfer of power plant emissions from one area to another. Finally, the transmission system moves money. The first application of transmission was to connect remote generators to local distribution systems, to the customer load. As power systems developed, each area had its own independent power system, and each independent power system had its load and its generation and backup generation. The backup generation was necessary to supply load to the customers when the primary generation was out of service. It didn't take very long for people to figure out that if the power systems were connected by transmission, they could reduce the total amount of installed backup or reserve capacity by sharing reserves. Reducing the total reserves decreased the investment in generation and reduced the price or the cost of electric power. These concepts are easy. I'd like now to talk about some more difficult ones. First, it's important to understand that electric power transmission is not transportation. The transmission system is not a transportation system. Here's a transportation system. In a transportation system, something is created and loaded at point A. Sometime later, it's moved unchanged to point B. The path that the product follows is known, it's controllable, and the transportation capacity of trucks, pipelines, etc. is easily measured. None of these 4 statements is true of electric power transmission. That's because transmission is not transportation. If electric power transmission isn't transportation, what is it? Transmission is a force at a distance function. It's like a teeter-totter. In a teeter-totter, end A goes down and end B goes up, but no thing is transported along the board from A to B. Transmission changes the properties of electricity. The properties of electricity at the power plant are different from the properties of electricity seen by the consumer. There are multiple sources and sinks. An electric power grid is complicated. There are power plants located hither and yon, and generation at various points on the grid. And all of these multiple sources provide power. The multiple sinks extract power from the grid simultaneously. In transmission, creation, transmission, and use of electric power are simultaneous. It's hard to store power. The transmission system as a whole takes part in every transaction, not just a single A to B path. When a product is moved by truck from a factory to a store, you can trace the progress of the truck along the highway system, and you can determine exactly which roads the truck uses. In electric power transmission, the quote truck, close quote, in essence uses the whole highway system simultaneously. Flows on the transmission system are generally not controlled, and they're not traceable to specific transactions. Oh, sure, you can hang a meter on a line and measure the flow on the line, but you can't tell where the power came from, and you can't tell where it's going. Finally, and remarkably, there is no simple measure of network capacity. This statement should be surprising. If we can't measure capacity, how close can we get? Well, this is about the best we can do. Transmission or transfer capability or capacity, the terms are used interchangeably, is, loosely speaking, the maximum amount of power that can be injected at A and simultaneously extracted at B reliably. Here is an example. This is from a study of the eastern part of the United States. The area labeled as MAC at the upper right-hand corner consists of Pennsylvania, New Jersey, and some other nearby states. South of that are Virginia and the Carolinas. To the west, the Tennessee Valley Authority and some surrounding areas, and in the upper left, Ohio and states and portion of states around it. Each pair of areas has three numbers associated with it. The center of the three numbers are the base case transfers of power from one area to the other, given the assumptions of the study. For instance, between ECAR and MAC, the base case transfers are 285 megawatts flowing from west to east. The upper number, the 1100 megawatts between ECAR and MAC, is the incremental transfer capability above the base case transfers of 285 megawatts. The maximal amount of power, in addition to the 285 megawatts, that can be transferred reliably between ECAR and MAC, going from west to east. The lower of the three numbers, the 5,000 megawatts, in the case of the ECAR to MAC transfers, are the maximum transfer capability, the maximum amount that can be transferred reliably from east to west, over and above the 285 base case transfers from west to east. These numbers are remarkable. One of the remarkable things about these numbers is they're very asymmetrical. How can that be? If it were an extension cord, for instance, between ECAR and MAC, you know that the capacity of the extension cord going from west to east is the same as the capacity of the cord going from east to west. The extension cord doesn't care which direction the power flows in. Why are the transfer capabilities different? Well, first, the transfer capabilities aren't just the sum of the capacities of the lines connecting A to B. Transfer capabilities are affected by the ability of each system to generate power and to absorb power. The transfer capabilities are affected by transmission lines that may appear to be remote to the interface between two systems. This is because the entire system is involved in every transfer of electricity. And between ECAR and MAC, the transfer capability may be limited by the overloading of a line down in Virginia or out in Tennessee or someplace else. Reliably loosely means without adverse effects in spite of the loss of any single element. That is, the 1100 megawatts of incremental transfer capability would continue or would not jeopardize the system, would not cause a problem for the system if any single element of the transmission system went out of service unexpectedly. Transfer capability is a limited measure of system capacity. It's limited because in the first place it's not a single number. A single number is easy to conjure with. Transfer capability is a vector. Furthermore, it's a vector of random numbers. Why is the transfer capability random? It's random because it changes as the load changes. The load goes up and down every day. And as the load goes up and down, the transfer capability changes. The transfer capability changes when generating units go out of service on forced outages or for maintenance. It changes when the dispatch changes. It changes when something occurs on the transmission system, the loss of the line, for instance, due to lightning. In addition, the transfer capabilities shown on the diagram of the previous slide are non-simultaneous. That is, they can only be considered one at a time. For example, the 1100 megawatts of incremental transfer capability between ECAR and MAC assume that the transfer capabilities between all of the other systems remain fixed, that the transfers among all of the other systems are fixed at their base conditions. You can't study simultaneous changes in transfer capability between two different sets of areas using this diagram. This diagram doesn't tell you anything about what you can do simultaneously by simultaneously exporting power, for example, from ECAR to MAC and from ECAR to TVA. The diagram is not useful, not helpful in studying that. There's a problem associated with transfer capability, a physical problem. The problem is called congestion. In real time, generators are dispatched optimally to minimize the cost of fuel. And this optimal dispatch considers losses. It recognizes that there are resistance losses on the transmission lines, but the economic dispatch ignores transmission constraints. If the optimal economic dispatch would load an element of the system over its capacity, the system is considered to be congested, and the generation needs to be redispatched. This redispatch will always increase the total fuel cost for the system. How does the planner see this problem? The planner says, well, let's consider system upgrades to reduce the congestion. The problem is that the economic benefit of an upgrade often won't justify the upgrade. Here's an example. The MAP line was a proposed 500 kilovolt line going from points southwest of Washington, D.C., due east, across the Chesapeake Bay, and terminating on the Delmarva Peninsula. The annualized cost of the line, sort of like the mortgage cost of the line, is over $200 million a year. The annual fuel savings due to reducing congestion are about a third of that. Obviously, the savings in fuel due to reducing congestion will not justify the cost of the line. So if transmission planners don't plan the system to eliminate congestion, why do they reinforce the system? They reinforce it for reliability purposes. Transmission planners test the future system, say 5 years out, in three major ways. First, they look for steady state overloads of lines and transmission and transformers, and for voltage problems. They do this using power flow software. They also checked for problems of electric currents under fault conditions using power flow and short circuit software. And finally, they look for stability problems by studying the power system dynamics by solving differential equations. So planners can test the future reliability of the system by carrying out simulations. But the question is, how much reliability does the system need in the future? Obviously, there's a trade-off. Obviously, if you invest more in building power systems and facilities, you ought to get a more reliable system. The problem is, we know that somehow a more reliable system has economic value, but we don't have a good handle on exactly how much that economic value is. We don't have a way to quantify with confidence the value of reliability in an electric power system. We can measure the costs associated with reinforcing the system, but we can't tell you what that reinforcement is worth in dollars and cents. So how do we resolve the trade-off between reliability and cost of investment? The answer is that a half a century ago, the electric power industry in the United States established an organization called the National Electric Reliability Council. The acronym is NERC. Later the Canadians joined, and so the name was changed to North American Electric Reliability Council, and the name's been changed again since, but always maintaining the same acronym. One of the things that NERC did was to develop consensus standards on how much reliability is appropriate and necessary and affordable for power systems. These standards were used on an advisory volunteer basis by utilities in both countries and have been adopted around the world. About 15 years ago, the U.S. Congress and the Federal Energy Regulatory Commission made these standards obligatory for U.S. utilities. What are the standards? First, there's the concept of violations. Violations means overloaded lines, or poor voltage, or instability, or loss of load. The standards consider several conditions. First, Category A. In Category A, all elements of the transmission system are in service and no violations are allowed. In other words, the system has to have flows on the transmission lines need to be below the capacity of each line, the voltages need to be correct, and so on, when all of the elements are in service. In Category B, N-1, any single element of the system is out of service, and no violations are allowed. This last sentence gets an asterisk. It gets an asterisk because there are areas, there are distribution systems, customers, who are served by only a single transmission line. Obviously, if the single transmission line goes out of service, they lose their power. The NERC standards do not require that every customer, that every distribution system be supplied through redundant transmission lines. The most common justification for reinforcing the system is a Category B problem. Category C is often tested as N-2, but it's really N-1-1. The way it works is you assume that some element of the transmission system is out of service, or goes out of service. The operator is given time to make adjustments, and after he makes his adjustment, a second element of the transmission system goes out of service. The operator doesn't know ahead of time what the first element will be or what the second element will be. In Category C, loss of load to customers is acceptable, but it has to be planned or controlled. You can't have cascading blackouts that cover a wide area of the system. There's also a Category D. Well, what does a planner do if he discovers that 5 years from now he'll have a violation in, say, Category B? Well, he examines possible fixes. How does he choose among these possible fixes? Well, usually planners choose the least expensive fix from among technically equivalent options. Where does the environment come in? Once they have made that choice, as they make detailed routing decisions, they generally fine-tune their preferred option to reduce the environmental impact. Let's sum up. First, what is the principal concern of electric power transmission system planners? What is the generally accepted measure of transmission system capacity? How does transmission planners determine if the system in the future will satisfy accepted standards? What do planners do if they determine that the future system will not satisfy accepted standards? Before saying goodbye, I'd like to make 3 more points. These are not in the textbooks. First, the average Johnson effect. If a business is guaranteed that it will be able to recover its investment, and if it is guaranteed a profit, and the profit is proportional to the investment, then the business has an incentive to gold plate. It has an incentive to overinvest if it knows that its profit will depend on the amount of investment and it knows that it will get its investment back. The average Johnson effect was one of the motivators of the restructuring of the electric power business in the United States and in many other parts of the world that occurred 25 or 30 years ago. This restructuring weakened the monopoly character of the power business and introduced elements of competition in an attempt to avoid the average Johnson effect. Second, reinforcing the network to reduce congestion may make the network more brittle. That is, it may make the network more susceptible to blackouts. I won't go into the details here. This is discussed in the 4th of the 4 lectures on power system planning. So this bullet is in essence an advertisement for lecture number 4. Third, economic evaluations of the benefit to the customer of transmission reinforcements are difficult to make for competitive locational marginal price markets. In modern competitive power markets, the price of electricity at a given point is the derivative, in the calculus sense, of the cost of providing that electricity. In traditional monopoly markets, the price of power at a particular point in the network was the cost of producing that power. There is a significant difference between the cost of producing power at a particular point and the derivative of the cost of producing power at that point. This significant difference complicates the calculations of the economic benefit of a transmission reinforcement. If you're interested in the details, your instructor can give you a reference that talks about this. This concludes Lecture 2. Thank you very much.